further to prove this theorem. Now let me start with the statement of this theorem, of this famous theorem. Uh, uh, so what is the statement? Statement is familiar to all of you, I think. The statement is like that. Just consider a polynomial so let us consider the polynomial equation where the polynomial is of degree n. Or equivalently, you can consider a polynomial with leading term 1 without loss of generality, so of degree n. Yeah. With the coefficients taken from the field of complex. From the field of complex. And the conclusion is that this equation must have a root in C. And if you can prove this, then you can easily show that this equation has n many roots by the theory of polynomial rings, division algorithms, etc. Okay. Now, the first attempt at proving this theorem was initiated by D'Alembert in 1746. But his proof was incomplete, and actually he assumed the existence of roots of this polynomial equation. And other attempts were made by Euler in 1749, Lagrange in 1772, Laplace in 1795. But these attempts also assumed the existence of roots. That is, they were assuming the existence of a splitting field of the polynomial. And so for this reason, their proofs were incomplete in view of this. Now at the end of 18th century, Gauss in the year of 1799, and before that James Wood in 1798, they were attempted to prove this theorem, although their proof had some gaps. Gauss, his proof has a topological gap, and Wood's proof has an algebraic gap. So in this line of ways of proofs, so these are incomplete. Okay. But the interesting fact is that Gauss and Wood, they didn't assume the existence of roots. That is important. They did not assume the existence of roots. Okay, so there are many other attempts have been made by mathematicians throughout the years, and so many proofs are there. We have already came across some proofs in complex analysis by using Liouville's theorem, by using maximum modulus principle, by using Roche's theorem, and also by using I think argument principle. And a rigorous proof was actually first published by Argan in 1806, and notably for the first time the theorem was stated for polynomials with complex coefficients rather than just considering the real coefficients. So he first stated the theorem for the complex coefficients. Okay. Now let us move to prove this theorem, the fundamental theorem of algebra, using fundamental groups of a circle. So let me begin with the equation that I have considered here. But I can do some transformation. I can impose some transformations here, because we choose first a suitable real number such that, and possibly it is large enough, because the condition I am taking is that the modulus of this plus lambda cube and a1 lambda into the power this plus a0 lambda to the power n, this is less than 1, by virtue of Archimedean property in R and by making lambda large enough to satisfy this condition. And you can easily do this because of these properties. Okay. So then we can consider the coefficients, just renaming them, such as bn minus 1 is an minus 1 by lambda, bn minus 2 equals to an minus 2 by lambda square, and b naught is a naught by lambda to the power n. And by this coefficients, you can transform the equation to this form: x to the power n plus bn minus 1, x to the power n minus 1 plus bn minus 2, x to the power n minus 2 plus b1x plus b naught equals to 0. So our aim is to show that this equation has a root. So our aim is to show that this equation has a root x naught in the field of complex. Yeah. Yeah. And if you can show this, then you will definitely have a root in the equation we have considered at the beginning. And that will be of the form. So the given equation will have a root lambda x naught. Yeah. So keeping these in mind, without loss of generality, let us consider the polynomial equation having satisfied the root, the condition, sorry. Yeah. Okay. So yes. So our aim is to show that without just considering the equation x to the power n plus n minus 1, x to the power n minus 1, n minus 2, x to the power n minus 2 plus a1x plus a naught equals to 0, with the condition modulus of n minus 1 plus modulus of n minus 2 plus modulus of a1 plus modulus of a naught is less than 1. and our goal is to show that this equation has a root. So our goal to show that this equation has a root in the unit ball. In the unit ball, okay, unit ball B2. Yeah. So this is our goal. Okay. So firstly, let us assume that the reverse case, that is the equation has no such root. And with this assumption, so if possible, let us assume that it has no such root. Yeah. Okay. And with this assumption, one can define a map. One can define a map K from the unit ball to the plane punctured at 0 by the rule Kz equals to z to the power n minus 1, z to the power n minus 1 plus a1z plus a naught. Yeah, good. With the additional condition that we have already specified, that modulus of n minus 1 plus modulus of n minus 2 plus modulus of a1 plus modulus of a naught is less than 1. Yeah. Okay, fine. And now we shall consider the map, the restriction map. So consider the restriction map H which is the map K over S1. And this means that H actually extends the map K continuously to the unit ball B2. To the unit ball B2. Yeah. Okay. Now, now our game is to show that. So our game plan is that H is null homotopic. Yeah. So what does it mean by homotopy of paths? So at this moment we need to introduce this concept, the homotopy of paths. Okay. So okay. So please, I have a call, so I need to receive this. Please give me 5 minutes. So, so okay. So, what does it mean by homotopy of two maps? So that I need to introduce, because without these facts, I cannot go further. Okay. So, what is the definition of homotopy of two maps are said to be homotopic from a topological space X into another topological space Y. So the definition looks like this. Let, if you consider two maps from a topological space X into another topological space Y, suppose f and f dash be two maps, two continuous maps, be two continuous maps. Yeah. Then small f is said to be homotopic to f dash if you can find out a continuous map capital F from the domain space is X cross the closed interval 0 1 to Y, such that the at 0 the map is Fx, and at 1 the map is f dash x for all x belongs to the capital X. Yeah. So this map uh, actually the picture looks like this. If this is f and this is f dash, so you are deforming this f to f dash continuously. That means that f, that capital F actually gives you a family of functions. That means for each t belongs to this, ft x is a continuous map from from x to y. Yeah. So you are getting a family of maps. So if you regard t as time, then you can say that at time 0 the map is f, and at time 1 the map is f dash. So you are deforming the map f onto f dash continuously. And this f is called homotopy. This f is called homotopy between these two maps, f and f dash. Yeah. And we can denote this fact as this. So f is homotopic to f dashed, means there exists a map from x cross the closed interval 0 1 to y, satisfying the property that at time 0 the map is small f and at time 1 the map is f dashed x. Okay, and whenever you are whenever f is homotopic to a constant map, then f is called null homotopic. Yeah, null homotopic. Yeah. So whenever f is homotopic to a constant map, uh, then f is called null homotopic. Yeah. So that is the function is deforming continuously to a point. Okay. Now this is the general definition of homotopy between two maps, continuous maps. Now I move to the definition of uh, homotopy between two paths. So the definition is quite same. Just okay. Look at this definition. So okay. So I know that. So a path is a path in a space, a topological space X is a continuous map from a closed interval AV into the space. Okay.
স্যার
Yeah.
তাই বলছি ধরুন হোমোটোপিক টু জিরোটাও কি অ্যাকচুয়ালি একটা নাল হোমোটোপিক বলা যেতে পারে?
বলো।
এই ধরুন একটা পাথ যদি আমরা যখন বলি হোমোটোপিক টু জিরো, ওটা কি স্যার নাল হোমোটোপিক একটা বলা যেতে পারে?
হোমোটপিক টু জিরো মানেটা কি বলো? ডেফিনেশন, হোয়াট ইজ দ্য ডেফিনেশন অফ হোমোটপিক টু জিরো?
মানে একটা পয়েন্টে সাং করবে পয়েন্ট।
মানে a point is a constant map, so it is null homotopy. Yes. Okay.
Actually, the meaning of null homotopy and the homotopy to zero are same.
Yeah, yeah,
আচ্ছা আচ্ছা
exactly.
স্যার, ঠিক আছে।
Yeah, yeah, good question, good question. Okay, so we consider the interval AB as 0 1. Okay, because any two closed intervals A and B is homeomorphic to the closed interval 0. So without loss of generality, we can consider the closed interval 0 1. Okay. Okay. So let us consider a space X, then two maps gamma and gamma dashed. Yeah. So two paths gamma and gamma dashed in the space X having same terminal points. Having same terminal points. That means it has the maps have same initial point and same end point. Suppose the initial point is small a and the end point is small b. Yeah. So this is gamma and this is gamma dashed. Okay. So then these two paths, gamma and gamma dashed, are said to be path homotopic in the space X if there exists a continuous map. If there exists a continuous map f from 0 1 closed interval to 0 1 to x, satisfying the property that the first one is at time 0 the path is gamma, and at time 1 the path is gamma dashed for all s belongs to closed interval 0 1. Okay. And f0t will be the endpoint A, the initial point A, and f1t will be the endpoint B for all t belongs to 0. Yeah, fine. So we call this f a path homotopy. So it is a homotopy between two paths. So that is why we are defining this as path homotopy between two paths, gamma and gamma dashed. And in that case, you write it as gamma is homotopic to path homotopic to gamma dashed. Just putting a p to distinguish the general fact with this one. So general homotopy and path homotopy. Yeah. Okay. So informally speaking, that I have already told you that gamma is, this means gamma is deforming to the path gamma dashed continuously, keeping their initial and end points fixed during the deformation. That is, yeah. So we are deforming this. So actually f will give you a family of functions for each t. Continuous functions, yeah. Okay. So these are the definitions of homotopy and path homotopy. And interestingly, these two facts will give you equivalence relations. That is the important basic theorem of this of these concepts is that these two relations and the homotopy and path homotopy, so they are equivalence relations. Equivalence relations in the family of continuous maps and in the family of paths. Okay. So let me have a look at the sketch of the proof of this theorem. Is just reflexivity and symmetry is very much easy. And for transitivity, you need to invite the important theorem that is called pasting lemma. And with the help of this, you can easily show that the relations are transitive. So first of all, if you look at the reflexivity, then so you can do this for any of this homotopy. So let me take this one, the homotopy, general homotopy, and take a map. So let us take a map, a continuous map. Yeah. Okay. So then you may consider, so suppose this is a map from okay, x to y. Yeah. So then you can define, so a map capital F from x cross close interval 0 1 to y by the rule f x t equals to fx. That is, at each time t, the function is f. And since f is continuous, so it is easily can be checked. It can be easily checked that capital F is continuous. So it is not so complicated. Yeah. So this f is a homotopy. So capital F is a homotopy between f and f, that is between f and itself. That is, f is homotopic to f, right? And similarly, if you consider the path homotopy case, you will definitely have this one also. So okay, so F is homotopic to F. Yeah. So this shows that these relations are reflexive. And for the symmetry case, okay, let us assume that, just consider two maps from X to Y, and let us uh, assume that F is homotopic to F dash. And that means you will find out a map capital F from X cross 0 1 to Y, uh, such that, sorry, such that, yeah, such that at time 0 it is F, and at time 1 it is F dash. Okay, okay, belongs to X. Yeah. Now, so our aim is to show that there is a map G from X cross 0 1 to Y with the property that at time 0 gx0 is f dash x and gx1 is fx, and the natural kind of map is that fxt goes to just make it reverse, that is t goes to 1 minus t, and with the help of this map t goes to 1 minus t, so this will give you, so the endpoints, so the maps f and f dash. So at time 0 it will be f dash, and at time 1 it is f. So f dash, f star of x0, this is f, and f star of x1, it is f dash x. Sorry, sorry, yeah, this one.
ভুল হচ্ছে, হ্যাঁ ভুল
Yeah,
হচ্ছে।
yeah. So f star x no x0 is f dash x, and f star x1 is fx. Yeah. So, and since f is continuous, so f star is continuous because t goes to 1 minus t is a continuous map. So definitely f star is a homotopy between f dashed and f. That is, f dashed is homotopy to f. Yeah. So this proves the symmetry case. Now, okay, and for the path homotopy also you can consider these maps. So this can be checked easily. So that is your task to do this on your own. So now the third case is to check the transitivity. Okay, transitivity. Yeah, this is not so complicated, but you need to invite the pasting lemma. Yeah. So let us assume that f is homotopic to f dashed and f dashed is homotopic to f double dashed. Okay. So by the definition of homotopy, you will have one homotopy from which will send f to f dashed, and another one to which will send f dash to f double dash. Okay. So f is the homotopy between f and f dashed. Yeah, and suppose f star is a homotopy between f dashed and f double dashed. So our aim is to construct a map which will send f to f double dashed, and for this reason what we shall do, so define a map G colon x cross 0 1 to y by gxt equal to. So what we are doing? We are dividing this interval into two parts, that is from 0 and half to 1. And from 0 to half we will accommodate the first homotopy, and from half to 1 we will accommodate the second one. And then we apply the pasting lemma, and which will give you a continuous map G. So this is our way of proof of this transitivity. Okay, so let me define. So gxt is fx to t for all t belongs to 0, half, and it is f star of x to t minus 1 for all t belongs to half, 1. So just we are dividing this interval and accommodate them together, and this map is well defined. And using pasting lemma, this G becomes a continuous map from x cross 0 1 to y. So this is your exercise to check the continuity of this map. This is very easy, but you need to check on your own. So this is an exercise to you. Okay. Okay. So hence this G is a homotopy between. Okay. So let me. Hello. So Gx at 0. So at time 0, what we shall get? If you get, so okay, so gx0 is fx0. Yeah. So what is fx0? F is a homotopy between f and f dash. So at time 0, f will give you the map small f. Now gx1, and that is, so since 1 is in this interval, so we will need to consider f star. So f star of what? So if we put this, so this is 1. So f star of x1, that is, f star is a homotopy between f dash and f double dash. So at time 1, it will give you the map f double dash. So in this way, you have defined a map, a continuous map from x cross 0 1 to y, satisfying these two properties of a homotopy. Yeah. So hence f is homotopic to f double dash, and this proves that the relations what we have defined is an equivalence relation. Okay. 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 Now,
ওকে অভিষেক, আমি একটা বলছি আর কি, ওপিনিয়ন দিচ্ছি
yeah, yeah.
যে তাহলে কমপ্লেক্স অ্যানালিসিস পড়তে গেলে হোমোটপি আগে ভালো করে পড়েই কমপ্লেক্স অ্যানালিসিস কে ভিজুয়ালাইজ
course.
ঠিকঠাক করা যাবে।
Of course.
অফকোর্স, ওকে।
Agree.
এগুলো কেসি, অ্যাকর্ডিং টু কেসি। হ্যাঁ, বুঝা যাচ্ছে, বুঝা যাচ্ছে। ওকে, কন্টিনিউ, খুব ভালো হচ্ছে, চালা।
Okay. Okay. So now I need to pose a problem to you, which will help us in our further discussions. That is a problem. That is, if you consider two maps f and f dash from x to y, and you consider another two maps g and g dash from y to z, to continue, these are continuous maps. Okay. And such that f is homotopic to f dash G is homotopic to G dashed. Then show that uh, G compose F is homotopic to G dashed compose F dashed. Yeah. Yes. So this is your exercise. Okay. Now let us have a look at an example. So, okay. So let me draw an example. Yeah. So let us consider the space X, which is R2 minus, that is punctured plane. So it is a punctured plane. Okay. Now consider two maps. The first one is Ft is cos pi t and Gt is cos pi t 2 sine pi t. Yeah. For all t belongs to 0 to 1. Okay. That is, we are considering one semicircle and another one will be, this is 1 and this is 2. So I think this one, right? Yeah. So one is F and another one is Z. Yeah. Okay. Now the plane is punctured at 0, 0. But these maps are path homotopic. Why? Because you will definitely have a homotopy which is very interesting, the straight lines, that is joining one point from a path to the another point of G through straight lines. So in this way you can say that F is path homotopic to G, because this deformation is continuous. The plane is punctured at 0, so you need not have any problem. Okay, but now I take the path H. What is H? H is cos pi t minus sine pi t. That means the lower semicircle. Yeah. Now you will get some problem because the plane is punctured at 0, 0. So you cannot invite the straight line homotopy because this point will not pass through 0, 0, because 0, 0. So we are considering the plane punctured at 0, 0. So this straight line homotopy cannot be accepted. And in okay, and further in later discussions we can show that actually you cannot have a path homotopy in between these two paths F and H. So F and H are not path homotopy because you cannot deform F, this F, past the hole at 0, 0 without introducing a discontinuity at 0, 0. Yeah. Okay. Okay. But if you consider the plane, whole plane R2, then definitely F and H would be path homotopic. So there will be no problem with that. Okay. So now I would like to define one more thing. Okay. A space X is said to be null, is said to be contractible, yeah, contractible if the identity map from X to X is null homotopic. Null homotopic. A space X is said to be contractible space if the identity map is null homotopic. That is, the identity map can be shrunk to a point continuously. This is a definition. And okay, so in view of straight line homotopy, and straight line homotopy can be you can have straight line homotopy in convex spaces, because in convex spaces you can draw lines between 2 points. So if you consider a convex space, then in a topological, okay, any topological vectors, in any topological vector space you can consider the straight line homotopy always, because between any 2 points you can draw a line. Yeah. So this is a theorem actually. This is a result. So any 2 paths can be made homotopic using straight line homotopy. Yeah. Okay. So a contractible space is defined as if we get that the identity map is null homotopic. Yeah. And also you can prove that. So you can show that a space is contractible, actually a contractible if and only if for any space A, for any space Y, any 2 continuous maps, f dashed from Y to X are homotopic. Yeah. So this you can check on your own, and this is very easy, not very much complicated. So this is an exercise. Rather, a space X is contractible if and only for any space Y, any 2 continuous maps f and f dashed are homotopic. So if you can show this, then you can definitely have a contractible space. Okay. And for example of contractible spaces, the closed interval 0, 1 is contractible. The real line is contractible. Why? Why these are contractible spaces? Because in these 2 spaces, the identity map is straight line homotopic to a constant map, because these are convex spaces. So you can always have this straight line homotopy between any 2 points. So just check on your own that the identity map is straight line homotopic to a constant map. And for this reason, these 2 spaces are contractible spaces. And also you have some important facts on contractible spaces is that the contractible space is path connected. So these are some basic problems. So I can write down the problem for your exercise, that show that a contractible subspace is path connected. And once you write this problem, you will definitely have the converse one. That is, does the converse hold? Right? So this is another good question. Does the converse hold? This is a question. So you need to find out. If it is wrong, then you need to find out a path connected space which is not contractible. Okay. Okay. And generally speaking, if you go for higher dimensions, you will see that n-dimensional Euclidean spaces and n-dimensional closed unit sphere in Rn, these are all contractible spaces by the use of same fact as we can do for the lower dimensional cases. And in fact, if you consider a convex subspace in Rn, then you actually have a contractible space. That is, a convex subspace in Rn is contractible. So these are all basic questions and exercises. Okay. Now, I would like to move to define the fundamental group, which will help us to prove our theorem of fundamental theorem of algebra. So actually, we will find out our goal is to find out the fundamental group of circle. Yeah. Up to now, we see the spaces like Euclidean spaces 0, 1 closed interval R, the unit sphere, closed unit sphere, or any convex subspaces. These are all contractible spaces. And okay, let me first define the fundamental group. Okay, so the fundamental group, yeah. So how to construct this is an important concept because, and actually we need to define these fundamental groups because the basic goal of general topology is to show that two topological spaces are homeomorphic. So this is a basic goal of general topology, that is whether the two spaces are homeomorphic or not. And this is the basic problem actually, yeah. And there is actually no tools and techniques or any kind of methods is there to solve this problem except some particular cases. Because showing two spaces are not homeomorphic, two spaces are homeomorphic. If you want to check this, you need to construct a continuous map, a continuous bijection which has a continuous inverse also. So this task is not very easy. And for that reason, so we are considering another way to view this problem. That is, two spaces, we are to check that whether two spaces are not homeomorphic. Yeah. So, okay. Okay. So if I have, for example, I can give you some example also. Okay. And yes, and to check this, that whether two spaces are not homeomorphic, what we did actually in the past, that we are inviting some topological properties, that is compactness, connectedness, etc. And as of now, uh, uh, the topological properties that we came across do not carry us very far, because, for example, you cannot show that R2 and R3 are not homeomorphic to each other with the help of the topological properties that we have studied in the past. And one cannot actually, yes. And another example is the surface S2. The surface S2, that is the unit sphere, and the torus, that is, and if you consider the double torus, just taking two torus and one disk, just take out one disk from each torus and then pasting them continuously, and this will give you the double torus. So these surfaces can be formed in the theory of surfaces. So the surfaces S2, the S2 and the torus T, and this one, the double torus, cannot be distinguished by the previously known topological properties. So for these spaces, we need to define simple connectedness, and which says informally that a space X is simply connected if every closed curve in X or every closed path in X can be shrunk to a point in X. Okay, and what someone has asked me a question that what does it mean by a path shrunk to a point? So actually the spaces that you are considering is simply connected. Okay, so simple connectedness, and this property will distinguish R2 and R3. Because in R2, the space, if you just take 1 point from R2 and take out one point from R3, then you will find that R2 is not simply connected, although R3 is minus that point is simply connected. And you can do the same thing for sphere and torus, but it will not distinguish the torus with this one, this and this. This simple connectedness will not distinguish these two spaces. So again, we have to run for a more general idea than simple connectedness, which involves certain groups, and that are called fundamental groups. And which includes the simple connectedness as a special case, for which the fundamental group becomes a trivial group. So that will be a special case. Okay, so let me start with the definition of fundamental groups, that is, and for this reason we need to define an operation between two paths. One is from some point x0 to x1, and another path will be from x1 to x2. That is, one is from x0 to x1, and another one will be from x1 to x2. So we are considering two paths. So f is a path from x0 to x1, and g is a path from x1 to x2 in a topological space X. Okay. Then we define a product of these two paths, f star g. Okay, f star g, which is given by, it is a path from the closed interval 0 1 to x by the rule. So f star g at t. So again we consider the same fact what we have considered in the proof of transitivity while we are proving the relation of being homotopy or path homotopy is an equivalence relation. Yeah. So that is, we divide the interval 0 1 into two parts, 0 half and half 1. So f 2t for all t belongs to 0 half, and g 2t minus 1 for all t belongs to half 1. Yeah. And using this definition again, you will see that by using pasting lemma, this map is continuous. And this will be a path from x0 to x2 in the topological, in the space x. Yeah. And if you want to check the well-definedness of this map, you need to consider two paths f and f dashed which are homotopic, and g and g dashed which are homotopic. Okay. Then you will see that f star. Okay. I am just doing this for paths. Okay. This will come later. Sorry. So this product operation on paths, this actually induces a well-defined operation of on path homotopy classes. That is actually the relation of being path homotopy has been proved to be an equivalence relation, and an equivalence relation will give you equivalence classes. So for each path you will find out, you can construct an equivalence class. So now we are to consider one path from x0 to x1 and another path from x1 to x2, and then considering their equivalence classes, and then you can define the binary operation on these two classes by the rule, the class f star g. That f star g is the path that we have defined here, which is a path from x0 to x2. Yes. And this operation you need to check the well-definedness of this operation. And for this reason, you need to consider two paths. One is f and another is f dash, which are homotopic to each other, and g dash, which are homotopic to each other. So f and f dash are both are paths from x0 to x1, and g dash are paths from x1 to x2. And then you need to check that these two will give you the same. Yeah. Left as an exercise. This is not so complicated. I have already.
স্যার এই ক্লাসটা আরেকবার বলবেন স্যার, এই ক্লাস অফ এফ জিনিসটা একবার বলবেন স্যার?
Okay. That is, for a given space, if you consider a family of paths in X and define the relation of being path homotopy on this family of paths, then this relation will going to be an equivalence relation on the family of paths, right? And if it is so, then this relation will give you equivalence classes of paths. That is, for a given path, you can have a class. You can construct a class. That is, this class is comprising of those paths which are homotopic to F. So this class consists of those paths in the space X which are homotopic to F.
Okay, sir. Okay, sir.
And okay, fine. So yeah, fine. So you can check on your own that this is a well-defined operation on path homotopic classes. Okay. I can give you a diagram also. Okay. So
Sir?
okay. Let me, yeah.
স্যার আমি বলছি স্টিরিওগ্রাফিক প্রজেকশনের উপর ওই হোমোটোপিকের ব্যাপারে কিছু বলা যেতে পারে, মানে কিছু কানেকশন, মানে আমরা যে স্টিরিওগ্রাফিক প্রজেকশনটা পড়েছি তার উপর পাথ হোমোটোপিক বা হোমোটোপিকের কিছু কানেকশন আছে, তাহলে একটু বলুন, জানা নেই এটা।
Stereographic projection is a different. Stereographic projection, yes. Actually, you are considering the extended complex plane. This and this will be homotopic to the surface S2, right?
হ্যাঁ স্যার।
So just you are doing everything in this surface. So taking any path from the surface, you can always consider the path homotopy between two paths, right?
আচ্ছা আমি স্যার হোমিও মানে হোমিওমরফিজম থেকে কিছু বলতে পারবো, মানে 1-to-1 যদি করসপন্ডেন্স একটা হোমোটোপিটা বোঝা গেল, তার হোমিওমরফিজম নিয়ে কিছু বলতে পারবো এটাতে?
কিরকম বলো, তোমার কোয়েশ্চেনটা কি?
মানে আমি বলতে চাই স্যার হোমিওমরফিজম নিয়ে কিছু বলতে পারবো কিনা এটাতে, যেহেতু ধরো এটা 1-to-1 একটা করসপন্ডেন্স ম্যাপ পাচ্ছি একটা, তাহলে এটা বলতে পারবো যে কন্টিনিউয়াস বাইজেক্টিভ আবার ইনভার্সটা কন্টিনিউয়াস এরকম ম্যাপটা পাবো, এরকম কিছু বলা যেতে পারে? আমার জানা নেই স্যার।
হোমিওমরফিজম বলতে কোন সেন্সে, মানে হোমিওমরফিজম কার কার মধ্যে হোমিওমরফিজম, মানে তুই S3
হ্যাঁ আমি
S2
এটা
নিচ্ছিস না,
স্ফিয়ারের মধ্যে।
S2 আর হচ্ছে এক্সটেন্ডেড কমপ্লেক্স প্লেন।
হ্যাঁ হ্যাঁ হ্যাঁ।
Actually,
obviously they are homeomorphic
yeah, these two spaces are homeomorphic. So what you are
by the choroidal metric.
Yeah. So what
Achha.
you are considering in C infinity, you can transform all these things to S2. There is no problem.
আচ্ছা স্যার ঠিক আছে।
You consider
Because
any
of
path.
homeomorphic.
Yes.
ওকে স্যার, হ্যাঁ স্যার ঠিক আছে।
আচ্ছা অভিষেক, আরেকটা প্রশ্ন, এই যে আমরা সেই পলিগন লাইন সেগমেন্ট নিতাম গামা টি ইকুয়ালস টু 1 মাইনাস টি ইন্টু Z1 প্লাস টি ইন্টু Z2 এরকম করে তো নিতাম, যখন ডিফারেন্সিয়েশন কমপ্লেক্স অ্যানালিসিসে দেখাবো ইউজ করব, সেটাও তো এরকম হোমোটপি থেকেই আসছে প্র্যাকটিক্যালি।
Yes, সেটাও তো একটা পাথ।
হ্যাঁ পাথ হ্যাঁ হ্যাঁ,
মানে ওটা হচ্ছে অ্যাকচুয়ালি ওই জয়েনিং পাথস,
হ্যাঁ জয়েনিং পাথ, ওই
নাম্বার অফ
x1
পাথস।
হ্যাঁ হ্যাঁ x1 থেকে x2 পর্যন্ত জয়েনিং নাম্বার অফ পাথস। হ্যাঁ
হ্যাঁ
হ্যাঁ, ওকে ওকে কন্টিনিউ।
Okay. 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 Now it should be noted that this operation that we have defined will satisfy the closure property. And the paths here, actually it has one condition is that one must have the endpoint x1, and which will going to be the initial point of the other path. Yeah, that is the endpoint of F will going to be the initial point of G. So that is a condition. That is, here you need to you have imposed that f1 is z0. And with these conditions, then you can say that the operation that we have defined, actually, it is a groupoid. It is a groupoid. Okay. Okay. And for other properties, that is for associativity and an existence of inverse. So how we can prove this? The proof is like that. Okay. So first of all, let us have a look on the associativity case. Yeah, associativity. Yeah. So for this reason, we need to consider three maps, three paths. One is F, another one is Z, and another one is H. So one path will from x0 to x1, another one will be from x1 to x2, and the third one will be from x2 to x3. Right? So this is F, this is G, this is H. Then what we shall do? Just define the products F star G star H. F star G star H. So the definition will be like that. So this map at T, so it is F of 4T for all T belongs to 0, 1 by 4. That is, we divide the interval again, and then it is Z 4T for all T belongs to 1 by 4 to half, and the last one is H 2T for all T belongs to half 1. Right? So this we can define, and this is the definition of these products of FGH. Now the another one is F star G star H. So similarly as in the above, we can define this as the first one will be F2T, that is for all T belongs to 0 half. The second one we can define it as G4T for all T belongs to half 3 by 4, and the third one will be like the above 4T. Yeah, that is from 3 by 4 to 1. Okay. So these are the definition of F star G star H and F star G star H. Okay. Now we consider a path in the interval 0, 1. K, which is from I to I, defined by K of T is S by 2, T by 2 for all T belongs to 0 half. It is T minus 1 by 4 for all t belongs to half 3 by 4, and similarly 2t minus 1 for all t belongs to 3 by 4 to 1. Then you can see that f star g star h, this map compose k is equal to f star g star h, and it is equal to f star g star h compose the identity map I. Now since k and I both are paths in the closed interval 0, 1, and the closed interval 0, 1 is a convex space, so k and I are homotopic, right? So k is homotopic to I in capital I, as capital I being a convex space. So you can always define a straight line homotopy between this k and I. Suppose, okay, in general you can consider a homotopy. So a homotopy, f is a homotopy between k and I. Yeah. Then you see that f star g star h, this is a path from x0 to x3, right? Yeah, in the space x, that is a map from the closed interval 0, 1 into x. So then we consider this map composed by f. Okay, then this will be a path, this will be a map from what will be the map 0, 1 cross 0, 1 to x. So this is a homotopy between, this is a homotopy between f star g star h compose k between f star g star h compose k, and the another one is f star okay, yes, yeah, oh, these two are same. Okay, so compose k, and another one is, okay, f star g star h compose I. Yeah, yes, fine. Using the problem that I have posed uh, in the beginning, yeah, that since k is homotopic to I, then you can say that, and this is a path from the closed interval 0, 1 to x, then composed with this, you can say that these two are homotopic using this map. This is easy. This is easy. This you can do at home. Yeah. But here you look at the functions, that is this one is f star g star h, and this one is this is actually f star g star h, because I is the identity. Yeah, fine. So f star g star h and f star g star h, these are homotopic to each other using this homotopy. So that means their classes are same. So this implies their classes are same because they are homotopic to each other. So their classes are same, and that is star g star h equals to star g. I put a bracket here, and this is h. Yeah. So in this way, you have proved that the operation is associative. So I think now it is 11:30, so I must stop here. So because I can prove the other properties of to show that the operation actually gives you a group on the family of paths having their initial points fixed, terminal points fixed. That is, we can consider the loops actually. So if you consider the loops, then you will see that the identity is unique. The left identity and right identity will be the same, and then you can check that the left inverse and right inverse also will be equal. And with the help of this, you can prove that the group, the set of all these loops based at a point, that is, if you consider a point x naught and you are considering the loops, okay, so you are considering the loops based at x naught, and it will form a group, and this group will be called the fundamental group, first fundamental group of the space x based at x naught. Okay, so that I can give you in the next session. So I must stop here. Any questions? Any questions?
Sir. Hello.
Yes.
Sir, the definition of simple connected, you say that an space is simple connected if every continuous map can be sunk into a point.
No. Every closed path.
Close rectifiable person. Close
No.
rectifiable.
No. Every
What
closed
is rectifiable?
Rectifiable means which length is measurable. That is, which length is bounded.
if you consider a closed path, so that must be rectifiable. Right?
Yeah,
Obvious.
of course.
You don't need to put extra word to anything which you are giving generally, right?
Okay, and also the null homotopy.
Huh.
Also in the definition of null homotopy,
Yes.
every continuous function
Yes.
can be sunk into a point.
Yes.
Obviously.
Yes.
So actually, what is the difference between these two types of definition?
What? Which one?
What the difference between these two definitions?
These paths are homotopic to 0. Yeah.
Then null homotopy is all any space where all the homotopy will be null homotopy, then this will be simple connected space.
Simple connectedness will be defined as the fundamental group will be the trivial group. That is every closed path, right? Suppose you are considering a closed path that is a loop based at some point. Suppose you consider a x naught, right?
Obviously, because
this loop
all the continuous path sunk to point, so that's why
will come to
the
the point x naught, the constant map at x naught.
constant map. Actually, the point is the actually defined as a function, so we must be considered as a function. So it must be considered as a constant function.
So this is ex naught. This is the identity of your group. So if the group is trivial, then you can define the space as simple connected. Okay.
Okay. Okay. Okay, sir.
Any
Sir?
question, suggestion? Yeah.
স্যার আরেকটা কোশ্চেন, যে যে কোনো ক্লোজড পাথ অলওয়েজ সাঙ্ক টু এ পয়েন্ট হবেই, মানে সেটাকে তাহলে সিম্পলি কানেক্টেড রিজিয়ন বলা হচ্ছে। তার মানে স্যার যেটা মাল্টি কানেক্টেড রিজিয়ন সেটা কি ক্লোজড হবে না, এটা বলতে পারি?
বুঝলাম না, মাল্টি কানেক্টেড মিন
মানে ওই আমি ক্লোজড মানে সিম্পলি কানেক্টেড যেটা বুঝছি, যে যে কোনো একটা ক্লোজড পাথ যদি সাঙ্ক টু এ পয়েন্ট যদি হয় তাহলে সেই রিজিয়নটা হলো সিম্পলি কানেক্টেড, তাই তো? তাহলে যখন স্যার মাল্টি কানেক্টেড আমরা যখন ইন্টিগ্রেশন করেছি মাল্টি কানেক্টেডের উপর, তাহলে মাল্টি কানেক্টেড আমরা বুঝি যদি মানে ক্লোজড হবে না সেরকম চিন্তা ভাবনা এলেই কি বলা যেতে পারে সেটা মাল্টি কানেক্টেড হবে? মানে ক্লোজড
মাল্টি কানেক্টেড মানেটা কি বলতে চাইছো? দ্য ইউনিয়ন, ডিস্টিংক্ট ইউনিয়ন অফ কানেক্টেড স্পেসেস,
মানে সিম্পল কানেক্টেড হবে না। স্যার আমি একটা বই পড়েছিলাম, মানে বলেছে ওরা মাল্টি কানেক্টেড এইভাবে ডেফিনিশন দিয়েছে যে
if you consider two connected spaces,
হ্যাঁ মানে সিম্পল কানেক্টেডটা ডেফিনিশন দিয়ে বলেছে যদি এটা না হয় তাহলে মাল্টি কানেক্টেড।
and if you consider a path, then the one portion is the suppose x1 and x2. So if you consider a path x in x1 space and another one is x2, then how could you say that this is a okay? Actually, I think the deformation will not be continuous. If the spaces are disjoint, then how can you define homotopy between paths? You can define homotopy between paths, but the paths are not homotopic. Because you cannot go continuously from one path to another.
Okay. Sir, ঠিক আছে।
Good question. Any questions, suggestions? Okay. So shall I stop?
Yes, sir. Thank you, sir.
থ্যাংক ইউ স্যার, সুন্দর লাগলো।
ওকে ওকে অভিষেক, ঠিক আছে, ভালো হয়েছে।
বোঝা গেছে তো অরূপদা?
হ্যাঁ, বোঝা গেছে। এবং এটার পুরো অ্যাপ্লিকেশনটাই কমপ্লেক্স অ্যানালিসিসই হচ্ছে, ফুল অ্যাপ্লিকেশনটা।
অবশ্যই।
প্র্যাকটিক্যালি কমপ্লেক্স অ্যানালিসিস করার জন্যই আমাদের অ্যালজেব্রিক টপোলজি পড়ার দরকার, সত্যি কথা।
একদম।
হ্যাঁ, নইলে কমপ্লেক্স অ্যানালিসিস এইভাবে ভিজুয়ালাইজ করা যাবে না।
আচ্ছা, হ্যাঁ সেই একদম সেটাই।
ওকে বাই।
প্রমাণটা আবার দেবো। হ্যাঁ ঠিক আছে।
হ্যাঁ।